Lecture 11, Energy, Resources and Alternatives. We've seen that humankind's energy use is the predominant reason for our influence on Earth's climate through the combustion of fossil fuels and the production of greenhouse gases, particularly carbon dioxide. So if we're going to do something about human alteration of climate, if we're going to slow that or stop that process, we need to do something that keeps the carbon dioxide generated from fossil fuels out of the atmosphere. I'll talk about some alternatives that might still involve fossil fuels in the next lecture, but for now, the most obvious thing we could think of doing is replacing fossil energy sources with other sources of energy. So this lecture is a survey of some of the other energy sources available to us. And I want to take a realistic view of those sources, something I think doesn't always happen. I want to look at particular energy sources and see whether there is really enough there to supply that colossal energy consumption that I described in the previous lecture, and also to ask whether we have the technological and economic means to extract energy from some of the other sources that are available to us. So the question is, what are some of those other sources? Well, I want to get very fundamental about that, and I want to take a look at Earth's energy resources. So let's look at a diagram that depicts the flows and fuels that make up Earth's energy resources. Once again, flows are streams of energy that come to Earth and flow around through the Earth system, and we can tap into those streams of energy. Fuels are substances that store energy, materials that have energy locked into their chemical or nuclear structure, and we can extract that energy. So let's look at these fuels and flows. What are Earth's actual energy resources? So the diagram I'm showing you has a huge arrow coming in at the upper left. That's the solar flow, the flow of solar energy to planet Earth. And that flow constitutes 99.98% of all the energy arriving at the Earth system. That's a big number. Solar energy supplies virtually all the energy that comes to planet Earth. So when we talk about our energy resources, at least energy flows, these streams of energy that we can tap, the dominant energy flow to planet Earth is solar energy. Remember that when someone tells you there isn't much solar energy and solar energy isn't a viable alternative. The rate at which solar energy reaches Earth from the sun is a little bit more than 10,000 times that 15 trillion watt energy consumption rate of humankind, of civilized humanity. That's 10,000 times more energy than we human beings use is coming to the Earth from the sun in any given time. The solar flow is huge. It's 10,000 times humankind's energy consumption, and it is the vast majority of the energy that comes to the Earth system, 99.98% of it. And this diagram I'm showing you talks about those flows in terms of percentages of the total amount of energy coming to Earth. So the solar flow is 99.98% of the energy coming to the Earth system. We found already that about 31% of the solar energy is reflected directly off the Earth, off the clouds, off ice caps, off snow, off deserts, and so on. And so 69% of the energy coming to Earth is solar energy that actually gets into the Earth system without being reflected off. What does that energy do? Well, it drives a number of subsidiary flows. For example, 45% of that solar energy that comes into the Earth atmosphere system gets converted into thermal energy, the energy of warmed things, mostly the surface of the Earth, but also to some extent the atmosphere. Some of that energy, about 23%, goes into evaporating water from the ocean and other surface waters, and that energy gets stored temporarily in the atmosphere in the form of water vapor. I talked about that before, how water in the vaporous state contains this latent heat, this latent energy associated with the fact that it's been converted from a liquid to a gas, and we could get that energy back if we recondensed it into a liquid, or nature can get that energy back if nature recondenses it into a liquid. About 1% of the incoming solar energy ends up driving the winds and the ocean currents. Only about 1%, but that's still 100 times humanity's energy consumption goes into driving winds and ocean currents, making the movements of air and water that constitute those currents. Very tiny fraction of the incident solar energy, about 0.08%, 0.08%, almost 0.1%, almost 1 part in 1,000, but not quite, is the energy that's captured by living plants, by green plants, through the process of photosynthesis. And that energy flows from the plants into dead material. When the plants die, it flows through the animals because all animals are dependent ultimately on plants for the source of their energy. And it flows out of the life system through the decay of dead matter and waste matter. A tiny, tiny, tiny fraction of that energy that's been captured by plants, as I described earlier, is stored underground as the fossil fuels. And in today's world, there is also a flow of energy out of the fossil fuels. That's the 7 gigatons per year of carbon, an equivalent amount of energy you could calculate. It's about 0.007% of the entire Earth energy flow that comes out of the ground right now as fossil fuels are consumed and burned to human uses. There's a very small fraction of energy, about 0.0005% of the total energy flow, that is being extracted from the ground in the form of nuclear fuels and also driving human activities. There are a couple of other flows that we ought to talk about too. They're very small compared to the solar flow because the solar flow constitutes 99.98% of all the energy coming to Earth, but they are important. One is the geothermal flow. The geothermal flow is about 0.025% of all the energy coming from Earth. These are round numbers, so they don't add up perfectly, but they're close. The geothermal flow, about 0.025% of all the energy coming to the surface of the Earth, is coming from Earth's interior. And this is energy that has two ultimate sources, and geologists aren't absolutely sure how much is one source and how much is the other. But the two sources are the primordial energy that existed when the Earth first formed 4.6 billion years ago by the accretion of smaller bodies in the solar system that crashed together under the influence of gravity, heating up and giving the Earth its primordial heat. Some of that material included radioactive elements like uranium and thorium. Those elements, when they decay, produce heat. And some of that heat is coming from the decay of radioactive elements in the Earth's interior. So that's what keeps the Earth's interior warm. And that drives a very, very modest flow of energy to the surface, far smaller than the rate at which solar energy is coming in. A very small fraction, but that energy is significant, has some important effects on the planet. For example, it's ultimately what drives continental drift, which is a major process in reshaping the surface of the Earth, and as we've seen, also may have an influence on climate. Finally, and it also drives volcanism and processes like that that are also important in climate. Finally, a very, very, very tiny fraction of all the energy, 0.0017% of the energy getting to the surface of planet Earth, is coming from the mechanical energy associated with the rotation of the Earth and the revolution of the moon around the Earth, from the Earth-Moon system, mechanical energy of the Earth-Moon system. And what that mechanical energy does is drive the tides, sloshing the waters of the ocean back and forth, in most places giving us 2 high tides and 2 low tides a day. That energy is also available to us to harness, and that energy has a third distinct source, namely the mechanical energy of the Earth-Moon system. But it's a very, very, very tiny fraction of the overall flow. So let me summarize that in case you came into this course or this lecture thinking, gee, there are all kinds of energy sources out there that we human beings can exploit. Let's just try exploiting different ones. Well, the answer is not quite so simple. There are really only 3 sources of energy to planet Earth, ultimately. One are the solar flow, energy coming from the sun. One is energy coming from within the Earth. That includes this geothermal heat, and it also includes energy stored as fuels inside the Earth, some of which are fossil fuels, which ultimately came from sunlight, and some of which are nuclear fuels, which were built into the nuclear structure of the materials from which the Earth formed. And finally, we have the tidal flow. So that's it. There are really 3 fundamental sources of energy for us to use. And we want to talk about those in realistic terms, about how we might use those to replace the fossil fuels that produce the carbon dioxide that is largely but not entirely responsible for human-caused global warming. So let's take a look at some of these fuels. We know, or some of these flows also, we know in many cases how to tap into the flows or how to take the fuels and convert that trapped energy into energy we would like to use for transportation, for heating, for industrial processes, for generating electricity, for refrigeration, for cooling, for all the things we do with energy. In some cases, we have the technologies for doing that. In some cases, the technologies are very mature and economical, and in other cases, the technologies are developed, but they aren't developed to become economically viable yet, and in other cases, we simply don't yet have the technologies. Furthermore, some of those sources are more than adequate to supply our energy needs, and some are not. So let's begin by looking in a little more detail at the source of energy we now use to supply most, that is about 87% of the world's energy needs, and that, of course, is the fossil fuels. Well, we know how to get energy from fossil fuels. We burn them. When we burn them, we combine the carbon in the fuels with oxygen to make carbon dioxide, and we combine the water in the oxygen, the hydrogen in the fuels with oxygen to make water. So CO2 and H2O are the products of fossil fuel combustion. By the way, how much we get of each depends on the fossil fuel. Natural gas, CH4 methane, is got more hydrogens than carbons, so more water forms when burning methane and less carbon dioxide. Coal, in contrast, is mostly carbon and so forms mostly carbon dioxide, and oil is somewhere in between. That's why on a per unit of energy generated basis, natural gas is a better fuel in terms of its climate impact than is coal. Coal is the worst in that term. And here I want to make a distinction that I think is often muddied. People talk about coal as a dirty fuel. Coal is a dirty fuel. It produces a lot of other pollutants. Mercury, sulfur, other compounds that come out in the burning of coal are pollutants in the traditional sense of being toxic materials that are harmful to us or the environment. But coal also produces more carbon dioxide than the other fossil fuels per unit of energy produced, and I don't want to call that dirtiness, because when we burn a fossil fuel, what we want to do is to create carbon dioxide. Carbon dioxide is not an incidental byproduct that we could remove, that we could avoid, like sulfur is from coal, or mercury. Those are things that happen to be in the coal that we could either remove or trap after burning, but carbon dioxide is the essential thing we want to make when we burn coal or other fossil fuels. So in that sense, it isn't a pollutant in the usual sense. It isn't a harmful byproduct that doesn't really have to be there, like a toxic contaminant. It's the thing you want to make when you burn a fossil fuel. So keep that distinction in mind when somebody says, well, one fuel is dirty and one fuel is clean. Well, are we talking in a climate sense or are we talking in a pollution sense? Sometimes those two things go hand in hand, but sometimes they don't.